Alright, so today we are going to talk about infinite geometric series. So we've talked about geometric series, and those are series that have a common ratio. Today we're going to look at infinite geometric series. And remember, series is always a sum. So let's start with a quick example. Okay, so my example is find the sum. We have the series from n equals 0 to 3 of 2 times 2/3 to the n. So I'm just going to start by writing out the terms of this. So starting with 0, anything to the 0 is 1. So my first term is going to be 2. Second term, this is going to be to the 1. So 2/3 to the 1 times 2 will be 4/3. This squared is going to be 4/9 times 2 will make it 8/9. And then if we plug in a 3, we're going to get 16/27. Okay, so this is finite. Okay, there are 4 terms in this sequence. And if we add them up, and you can just type them in your calculator, you're going to get 4.81. So let's find the sum a different way. So this is a geometric series. If you look, we have a common ratio of 2/3 that we're multiplying to get from term to term. So rather than just physically adding 1, 2, 3, 4 terms, I'm going to use the sum of a geometric formula here. So my A1 is 2, so we're looking at this series, minus 2. My R, my common ratio, is 2/3. We're going to raise that to the, if I want 4 terms, raise it to the 4th, and that's going to be 1 minus 2/3. Again, we can plug that into the calculator, and we will get 4.81. So just to confirm, I'll show you what we had typed in the calculator for each of those. So we have the 2 plus 4/3 plus 8/9, those 4 terms added together gets us 4.8148. And then the same thing using the sum formula, and we get the same exact thing. So what if rather than a finite series, so starting at 0 and ending at 3, I start at 0 and I go to infinity? How are we going to find this sum? Does this sum exist? How can we add an infinite number of things and get a number? Well, let's do some investigation. So what we're going to do is we are going to investigate what's called the partial sums. So I'm going to take that sum formula that we did, so 2 minus 2 times 2/3. We had it to the 4th, but now I'm going to look at it for any number. So I'm going to make this equal to x over 1 minus 2/3. Okay, so that is my sum formula. The only thing that's going to change is x, which is how many terms were added together. So we're going to use the calculator to help us do this. Alright, so I have plugged the formula into my y equals. So 2 minus 2 times 2/3 to the x, just make sure to open and close the parentheses there. And then 1 minus 2/3 is 1/3, so I just simplified that. So I'm going to first look at the table. So if we'd look at our table set, so second table, I just want to start at 1. We don't care about negative values, and my delta is just going to be 1 because we're physically adding terms. So 1 term, 2 term, 3 terms. So if we go to the table, okay, what we're looking at is what happens as we add more and more values. So here's my calculator. So if I add 1 term, we get 2, since the first term was 2. 2 terms is going to be 3.33, and so on. Our 4, so the one that we've already done twice in 2 different ways, we get that same 4.814. And then on, so we get 5.2, 5.4, so these numbers are getting bigger. So 5.9, 5.999, 5.999. So what I want you to see here is they're getting bigger, but they're not getting bigger very quick. So if we were to talk about a limit here, these values don't appear to be getting bigger than 6, and at some point, just by decimals rounding, we get 6. And it doesn't get any bigger than that. All right, so how can this be? How can a sum, we're saying from the table, this is equal to 6. How do we add an infinite number of things and get 6? Well, that's sort of interesting. So we're going to use limits to kind of look at how that happened. So I'm going to take this formula, and I'm going to look at the limit as x goes to infinity of 2 minus 2 times 2/3 to the x over 1 minus 2/3. Okay, I'm going to start by factoring out the 2. So I'm going to have 2 minus, that leaves me, 2 times 1 minus 2/3 to the x over, we'll go ahead and just call that 1/3. Okay, I'm going to pull this section out because this is just a constant. This is just a constant. This piece is the only thing that's going to change as x goes to infinity. So if I look at what happens to just that piece, as we go to infinity, well, 1's just going to go to 1. But 2/3 to the x, we investigated limits earlier here. 2/3 to the x is going to go to 0. So this whole thing is going to be 1 minus 0, which is 1. So in this formula, as we go to infinity, this whole piece goes to 1. So that's going to leave me with the limit as x goes to infinity of 2 times 1 over 1/3. And that's all just a number. So 2 times 1 is 2 divided by 1/3 is the same as multiplying by 3, which gives me 6. So the key to this whole thing is this piece right here. The fact that that went to 1, and that happened because 2/3 to the x went to 0. So any series that has this, otherwise known as the common ratio raised to the x goes to 0, then we can find the sum doing all of this. Okay, so if the limit as n goes to infinity of the common ratio raised to the nth power is 0, and we'll talk about what conditions that happens in. That means 1 minus r to the n is going to equal 1, right? Because if it's 1 minus 0. So let's look at the sum formula. So Sn is a1 minus a1 r to the n over 1 minus r. This is equal to a1 times 1 minus r to the n over 1 minus r. Well, this piece here, 1 minus r, is equal to 1. So all we're left with out of this is a1 times 1 over 1 minus r, or a1 over 1 minus r. So the sum of an infinite geometric series is going to be this formula here, because this piece, if the certain conditions are met, is always going to equal 1. So let's talk about how this is going to happen. So we're taking the common ratio, we're raising it to an infinite power, and it equals 0. Well, that's going to happen if my ratio, if this number is something in between -1 and 1. Okay, so we talked about limits here earlier in the lesson. And if I have something like the 2/3 raised to the nth power, it's going to get infinitely small. Versus if I have something like 3/2, then it's just going to keep getting bigger and bigger and bigger. And this piece will not go to 1, so we can't find the sum. So the sum of an infinite geometric series is this only if this condition is met. So the bottom line is the sum of an infinite geometric series, S, so notice that we no longer have an n here because I'm not adding a specific number of terms, I'm adding an infinite number of terms. So the sum of an infinite geometric series is a1 over 1 minus r, super simple little formula, if and only if the common ratio is between -1 and 1. So the sum of an infinite geometric series is a1 over 1 minus r if the common ratio is between -1 and 1. Now, some of you guys are sitting here going, no, we're adding an infinite number of things. You can't add infinite number of things and get a finite value. So I'm going to show you an example that if you are not convinced, hopefully you will get convinced. So I'm going to talk about the number 1/3. Okay, so you know that 1/3 is equal to 0.333333 repeating, right? There's an infinite number of 3's here. So I'm going to take this and I'm going to rewrite this as 0.3 plus 0.03 plus 0.003 and so on. Okay, so let's take those decimals and turn them into fractions. So 0.3 is 3/10. This is 3/100, 3,000ths, 3/10,000ths, and so on. Well, what we have here is an infinite series. We have an infinite number of things. We are adding them together, and it is geometric because there is a common ratio that we'd multiply to get from term to term. So what is that common ratio? Well, if we look at multiplying, we'd multiply each of these by 1/10 to get from term to term. So let's use our sum formula of a infinite geometric series. So S equals a1 over 1 minus r. Well, my a1 is 3/10 over 1 minus my common ratio is 1/10. So that's going to be 3/10 over 9/10, which is going to be 3/9 because those 10s will reduce. And 3 over 9 is, drumroll please, 1/3. So we said 1/3 equals this, and then we turned this into a geometric series and showed that if I add an infinite number of 0.3, 0.03, 0.003s, I get a sum of 1/3. So you can add an infinite number of things and get a finite sum, and the reason is because the next 3 doesn't make the previous 3 any bigger. We're just adding numbers that are smaller and smaller and smaller and smaller, so it doesn't make the overall number bigger. So let's do some examples. So we're going to find each sum. So we've got 6/5 plus 4/5 plus 8/15. So my common ratio here is 2/3. Okay, and what we always have to check is 2/3 between -1 and 1, and it is. So we can find the sum. We just need a1, which is 6/5, and our common ratio, which is 2/3. So my sum is equal to a1 over 1 minus r, which for this one is 6/5 over 1 minus 2/3. So that's going to be 6/5. 1 minus 2/3 is 1/3. So that's going to be 6/5 times 3, which is 18/5. Now for you guys taking your quiz, the thing doesn't like fractions, so we're going to do the decimal equivalent of this, and then that's what you're going to enter to the nearest tenth. So this would be 3.6 as a decimal answer. For your test and things like that, fractions are absolutely fine, but for the quizzes, do that decimal. Here's my next example. So we're going to look from the infinite sum, so from n equals 0 to infinity of 2 times 3 halves to the n. When it's written in sigma notation like this, just because sigma is new and you're not necessarily going to know what this series looks like, write out some of the terms. So starting with n equals 0, we get 2. When n equals 1, we get 6 halves, and I'm going to leave it like that. When n equals 3, we're going to end up with 18 fourths. So this is an infinite geometric series, and what we want to look at is what is our common ratio. So when they're fractions like this, if we just look at what's on the top and what's on the bottom, so I'll make this 2 over 1, on the top we're multiplying by 3, and on the bottom we're multiplying by 2. So the fraction we're multiplying by is 3 halves. So this is an infinite geometric series. However, this number is not less than 1. Okay, it's bigger than 1. So there is no sum. You can also say does not exist. Okay, there is no sum. Now, it doesn't mean that you can't plug this number into a1 over 1 minus r and get a value. You will. It just is not going to represent the sum of this series, because this just keeps getting bigger and bigger and bigger. So it is not going to have a sum. Alright, so here's my next one. We've got the sum from n equals 0 to infinity of 2 times negative 3 to the n over 4 to the n plus 1. So again, writing out some of the terms so we can see what's going on. So if we start with 0, we're going to end up with a 2 on the bottom and a 4 on the top. We're going to end up with a negative 6 on the top when we raise this to the 1. We're going to have a 16 on the bottom. The next one, if I square it, we plug in a 2, that'll be 9 times 2 is 18. And then 4 cubed is 64. So this again is geometric. Its common ratio, if we look, is going to be negative 3 over 4. So that is between negative 1 and 1. So we're good. So we can find the sum by plugging it into a1 over 1 minus r, which for this one is going to be my a1, 2 fourths, is going to be 1/2 over 1 minus negative 3 fourths. So we're going to have 1/2 over 1 plus 3 fourths. That's going to be 4 fourths plus 3 fourths is 7 fourths. So if I multiply by the reciprocal, we have 4 sevenths times 1/2, which is going to be 2 sevenths is our sum. So if it's written in sigma notation, write out some of the terms so we can get a feel on what's going on. So this one, from 1 to infinity of 1 to the n. Well, if I write this out, we have 1 plus 1 plus 1 plus 1, which is geometric with a common ratio of 1. And I've written the common ratio as between negative 1 and 1 non-inclusively, and this example should help illustrate why. If I'm going to add an infinite number of 1s together, we're not going to come up with a sum. We're going to have 1, 2, 3, 4. It's just going to keep getting bigger and bigger. So again, this is no sum because the ratio is not between negative 1 and 1. It is 1. All right, so bottom line is if you have a geometric series and the common ratio is between negative 1 and 1, you plug it in the formula. If it's not, there is no sum. So past that, we just start making the series look a little bit more complicated, but there's nothing here we can't do. So before I look at what this series really is, sine of pi over 6. Sine of pi over 6 is 1/2. So what I have is 1/2 squared to the n. Well, that's just the same as 1/4 to the n. So if I were to write that out, now this looks a lot easier. So I plug in a 0, we get 1 plus 1/4 plus 1/16, and so on. So again, we have a infinite geometric series. So a1 over 1 minus r, because our common ratio is 1/4. So this is going to be 1 over 1 minus 1/4. So that's going to be 1 over 3/4, which is 4/3. So again, just increasing the complexity of what we're dealing with here. So this one, the trick is we're not starting at a number, I'm starting at a variable. So if I were to write out this series, my first term would be 2 times negative 3/4 to the x. My second term would be 2 times negative 3/4 to the x plus 1, because we're just increasing that by 1. Okay, and so on. So we're just adding 1 to this. So this is the geometric series, because what we're doing is we're multiplying to get by an additional negative 3/4. So my common ratio is negative 3/4, which is between -1 and 1. So my sum is going to equal a1, so this guy here, over 1 minus negative 3/4. You could leave it like this. I'm going to simplify it a little bit. So this is going to be 2 times negative 3/4 to the x over, this will be 4/4 plus 3/4 is 7/4. So if I copy that, flip there, or multiply by the reciprocal, we're going to have 8/7 times negative 3/4 to the x. So our answer just ends up with an x in it, but that would still be the sum. All right, last example. So write the first 3 terms of the IGS. You're going to see me abbreviate this more and more. That stands for infinite geometric series, where the first term is 4 and the sum is 16. So using our sum formula, I know the sum is 16 and a1 is 4, but what I need in order to write the progression is the ratio. So if I multiply over here, I'm going to have 16 minus 16r equals 4. If I subtract 16, we get a negative 12. So r is going to be 12 divided by 16, which would be 3/4. So once I have that, I can write the series. So my first term would be 4. The next term is going to be 4 times 3/4, which would be 3, times another 3/4 is going to be 9/4. And those would be the first 3 terms of that series. So infinite geometric series, kind of an interesting thing. Hope you learned a lot about it.